All right, good afternoon. This is the first class of TELE 1022, Telecommunications 1022-25 Fall, Fanshawe College, London, Ontario. All right, there we go. Here's the opening statement. Along with the opening statement for the lab, I'm going to ask you to print the first lab. And yes, it's going to be the equipment familiarization thing. We need to make sure that we have all the dots over the I's and the dashes over the T's. Is that what they say? When it comes to doing the labs? Because as I keep saying, there's nothing worse than trying to learn how to use the equipment while doing the lab. We're missing the whole thing that the lab is supposed to teach us. Okay. All right. I don't think people are rolling in already anymore. 21 people. I think the class is 22. So we're missing one person. So that's pretty good participation, I would say. All right. Here is the class. F5 stands for the. All right. I think we got this whole thing going. Now, my style of doing the presentation is, well, some people read, some people display the text while talking. Sometimes I'm going to read and I'm going to stop and explain, and sometimes I'm going to show you the pictures. But I think there's nothing worse than me displaying the text and talking over that. So you're trying to read and you're not getting it because you're trying to listen, and then you can't hear me because you're trying to read. So I think I worked out a pretty good balance when it comes to that kind of stuff. If there's anything that that you would like to see more or less, just let me know. All right. So module one, telecommunications circuits. That's the first slide, is it? Yes, it is the first slide. All right. So circuit blocks in telecommunications vary widely. Well, here's a statement. However, there are some common circuits used in most communication systems. So we'll be talking about the model of the communication concept. These circuits might be passive, such as resistor, capacitor, etc., or active as a transistor, op amps, operational amplifiers, and well, etc. What does this mean? That the passive circuits or passive components are the components or circuits that do not require power to work. Like, for example, a microphone, well, not all the microphones, but let's say a dynamic microphone is a passive circuit because it does not require power to be supplied to it in order for that to operate. Okay? Resistor is a passive component because it does not need external power in order to work. We just put that in the circuit and it does its job. Now, as we're going to go along, it's also going to be, are these PowerPoints going to, yes, they're going to be posted. I'm just posting those after the class. Okay. Because sometimes we just we are not well, we're going to have those PowerPoints. Like for example, I'm not going to go through the whole thing today. We're going to leave some for the last hour on the on Friday. Okay. But if there's something different you would like, it makes your studies better, let me know by all means. Right? So passive versus active components. So we just talked about resistor, capacitor, or a diode. These are passive components. Microphone is a circuit because it does have some additional parts in there. It's a passive dynamic microphone. Now, for example, a condenser microphone, that's a different story. It doesn't require external power, usually provided with the batteries. But sometimes mixing boards provide something that's called a phantom power. So that's another thing. There we go. Here's my laser, pseudo laser pointer. Now, the operational amplifiers are active circuits, as we're going to talk about those today as well. And those are called active circuits because in order for the operational amplifier to work, it has to have an external power supplied. Also, when I'm pretty sure you have done some logic gates labs that involve integrated circuits or otherwise chips. Um, um, you do need to supply power to, let's say, for example, an AND gate or AND gate. If it's a 7-pin TTL circuit, you need to supply the power to the pin 14 and the ground to pin 7. Then that makes it an active component or active part because power needs to be supplied, right? Now, these circuits may be analog or digital, but it's important to keep in mind that often the end user of the system is analog. Well, of course, for example, as humans, we have 5 senses to detect the environment around us, with those senses of hearing and sight being the most often used for our communication. Our senses are analog in nature. So if we use digital signal processing in any of the circuitry that we're going to use, ultimately at the end, there needs to be a digital to analog conversion for us to be able to receive whatever the message is. Okay. Now, modern smartphones use combination of analog and digital circuitry. Now, the early ones from like 70s and so on used only analog circuits. I think we have switched with all the technology with cell phones, smartphones, to pretty much digital, maybe about 10 years ago or something like that. And this is 2025 right now. So it's relatively not that long ago. But then again, it's not all digital because the little speaker or the earpiece has to be analog because it produces analog waves. So we can hear things with our ears. And the display has to, well, although all the circuitry is digital, it does have to provide an analog type of output for the light to be seen by our eyes, and so on. So that's this slide that we have. Oh, yeah, click. There you go. Communication system block diagram, a generic kind of a version of that. This is, well, most basic form of things, but we're going to take a closer look at certain aspects, or pretty much all of the aspects of this circuit diagram, the block circuit. Now, amplifiers, oscillators for carrier generations, and so on. So let's take a look at this thing here. We have a low frequency intelligence information and high frequency carrier in one sort of stage here. Now, in order for some communication systems to be channeled, like for example, well, radio stations or the radio, well, yeah, stations that provide our entertainment, news, and so on when you're driving in your car. Uh, those stations are on different channels. What does that mean? Well, the channels are determined by the high frequency carriers. A carrier is basically nomen omen, which is Latin for the name describes the purpose. It carries the channel. So usually be a high frequency, which is undetectable by us humans. Based on that high frequency, modulating that high frequency carrier by low frequency information or in the so-called intelligence signal, which would be the speech. For example, my speech would be an intelligence signal. Some people might argue, but I like that opinion. Let's say my speech is intelligent, okay? So it creates it possesses the intelligence signal, which is me talking. Could also be music, or it could be visual signals for television type of communication. Yeah? So low frequency is modulating the high frequency at the modulating stage or modulated stage. Now, all that is being amplified and sent to, well, a medium. It could be an antenna at the end stage of the amplifier, and the signal is going to be carried by the space or the air, so electromagnetic waves. Or it could be other mediums. It could be fiber optics, it could be copper, and the copper we just referred to as the metallic type of mediums, such as wires, metal wires, and usually it's copper. So just for the simplicity of things, we call that copper. Even if it's aluminum, we call it copper. So that modulated signal is being carried, or the modulated carrier, the carrier that's modulated by the intelligence is being modulated, well, combined, or the technical term is mixed. That's the mixing stage, because the low frequency intelligence is mixed with the high frequency carrier. Now that carrier is modulated carrier is being carried through whatever medium that is, fiber, copper, or air, and then is being picked up by whatever receiving stage, and the receiving stage is going to be tuned to the carrier frequency. The best way to describe would be if, like, for example, you would have a flashlight or torch if you were in England. If you had a flashlight and you were flashing your message, let's say with the Morse code, but you're flashing that through a green filter. All right. So at the other stage of at the receiving end, there will be a receiver that only can see a green light. All right. And that those flashes that the green light is producing, only the green light is being received and processed. Now, at the same time, there could be other flashlights going through other different filters. Could be red, blue, whatever else color. And on the other end, whatever the receiver, they would decide whether to only see green light or only see yellow light or only see blue light and so on. And that will only be the message received. But in the air, all those lights are being mixed and all those messages are being sent at the same time. So the same thing with the carrier. So with the light, when we change the frequencies of light, we are going to distinguish those changes by different colors. When it comes to high frequency, in megahertz, for example, or in kilohertz, light, by the way, would be in terahertz. So that's a completely different region of frequencies. So let's say we have megahertz or kilohertz. Those will be electromagnetic waves carried by the air, for example, through the antenna, or maybe through a concentric cable, or also called coaxial cable, with the designation of RG. RG stands for radio guide, and could be whatever cable that internet to your house is being provided by just by that. The internet signal is in an analog form that travels through the cable that goes to your house. Then the modem basically demodulates that and converts that into digital Ethernet type of protocol signal. Then the Ethernet is carried through your equipment at home. And then whatever you are producing as a signal, then the modem modulates that and sends it out. So modem is a bidirectional device, and its purpose is to modulate and demodulate, and those two words are combined into modulate, demodulate, so modem. Okay, I bet some of us didn't know that. All right, so then those the receiver is going to be tuned to that particular carrier of the frequency, and it's only going to detect that carrier. And since the carrier is modulated, it's going to take the whole thing, that modulated carrier, and it's going to, at this demodulator or decoder stage, it's going to strip the carrier because it's not needed anymore, and the carrier is much higher frequency. So if we modulate the extremely high frequency with extremely low frequency, then the high frequency becomes sort of like not obsolete, but not noticeable to us. And that carrier is going to be stripped from that signal, and only the intelligence signal is going to be sent to the amplifier and to the output transducer. Right? What is a transducer? A transducer is a device that converts one form of energy into another. Like, for example, a loudspeaker, which is basically a speaker, but the proper name for that is called loudspeaker, converts the electrical signals into the longitudinal vibrations of the air, which we receive that as sound. And of course, over here, it's not shown, but there would be something that's called an input transducer, which would be a microphone, the microphone to which I am talking, okay, for example. All right. So that's basically the whole model of the whole transmission system, and there could be some subsystems that are using those this model within the huge model. So that can be layers of the same thing. All right. Like, for example, if you have a wireless microphone that is connected to the mixing board, the wireless microphone, it will have that, the whole thing, just to put the sound, just to convey the sound into the mixing board, audio mixing board. It will have the input transducer, it will have the carrier, and it, because the carrier is going to be connected with the receiver of the wireless microphone, and that is going to be modulated, the carrier, with the speech, and it's going to be amplified, sent over a little tiny antenna, and through the air, which is going to be our medium, it's going to go into the receiver of the wireless microphone. It's going to be demodulated, and it's going to have the sound only, just the intelligence, is going to send to the mixing board. And mixing board, again, will be part of the whole system. So the input of the mixing board becomes this stage again. So it's basically kind of growing, building itself. So we could have this system within the system, within the system, within the system. All right. So we were talking about amplifiers. Amplifiers do amplify signal. Oscillators, which would be the carrier generator. In order for us to produce a carrier frequency, we need to have something that produces that carrier frequency. And oscillator is the device, just the device to do it. We're going to have an oscillator oscillating at certain frequency, just like producing the color of the light, but we're not talking about the light now. Well, we could, but we're talking about the frequencies right now. It's going to create that high frequency, and that low frequency intelligence is going to modulate that. It's going to put it in a different shape, and we already talked about that. All right. So oscillators are the things that generate the carrier. We will talk about the oscillators furthermore. Modulator and demodulator, there will be different type of circuitry that we're also going to study. Then the information and the voice or data, and or data. That will be the intelligence signal here, right? The output transducer and the input transducer, we already talked about that. And this is transmission medium or transmission medium, which is the environment for the signal to travel. And we go cable, fiber, or free space, so copper, fiber, or air, right? And here's a reference to where this image is found. If you click on that later on, it's going to take you to the link where our textbook is to be purchased. Okay? Now let's talk about linear and nonlinear circuits. All right, let's see here. Both linear and nonlinear circuits are used in telecommunication circuits. Here's an opening statement. All right. So linear and nonlinear circuits are being used. Right? They exist, so they are being used. It is important to understand the difference and how the circuitry can be applied. All right, linear circuits. In linear circuits, the relationship between the voltage and the current is constant. You get a straight line. In just a regular DC type of circuit, when you have a power supply connected to a resistor, maybe connected to another resistor in series, and then closed loop. If you measure the voltage over one resistor, it's going to be proportional. The changes in voltage are going to be quite proportional to the changes in current of the inside, well, in the circuit or in the resistor. So across the resistor, if the current increases, the voltage increases automatically. So you're going to have something like a straight line going on. So this would be a linear circuit. Let's say that I missed something. The values of resistance, inductance, and capacitance do not change. A resistor in a DC circuit is a resistor in DC and AC. Now, sometimes people confuse the reactive circuits with nonlinear circuits. And in a way, maybe they could be considered as such, and sometimes I cross the line one way and the other. Well, you have a capacitor and a coil, or let's say there's a capacitor, resistor in series, and all that is connected to an AC power supply this time. Let's say the AC power supply provides whatever voltage of a signal and well, AC signal, and let's say it's 1 kilohertz. As long as the frequency stays the same, increasing the current is going to proportionally increase the voltage, or increasing the voltage across the component is going to proportionally increase the current, as long as the frequency stays the same. The frequency changes, then both current and voltage might change. But again, when you change the frequency, if you and then you change the frequency and you stay that way after that change, let's say you change the frequency from 1 kilohertz to 10 kilohertz, then the circuit is going to behave differently, because we have what's called reactive components. A reactive component is, like, for example, capacitor or a coil or inductor. They are going to behave in a different way if different frequency is applied. So things will change. But then again, as long as the frequency stays, you change the voltage, the current changes, and then again, you're going to get a straight line. Is it going to be a perfect straight line? Is there a circuit or component that's truly linear? Well, yes. Well, no. Okay. Because there are other factors that might decide how the component behaves. There's a temperature coefficient. The part would heat up and it's going to start behaving the other way. I mean, it's going to another way. It's going to conduct less, or it's going to conduct more, depending on the temperature changes. So things are kind of fluid. But in order to make sense out of things, so we could keep the sanity in calculations, we're going to call that linear circuit. Although in reality, things are fluid, things behave the way they behave, right? So there are going to be certain changes in behavior of whatever the components, as we're dealing with things in the reality of the reality. Okay. The values of resistance, inductance, and capacitance do not change. However, they might change depending on what's happening to them. The relationship between the voltage and the current might vary with frequency for frequency sensitive circuits, which is what we just talked about. But at a given frequency, this relationship is constant. We get a straight line. That's line, linear, kind of a circuit here, right? In nonlinear circuits, we don't get a straight line. These circuits do not have a linear relationship between the voltage and current. As an example, could be a simple diode. I'm pretty sure by now you have done some labs involving just a regular rectifier diode that you could pretty much remember that, let's say it's a silicon diode, then you reach the barrier or the voltage barrier. And as long as it's forward biased, the diode, then the diode doesn't conduct. You cross the barrier, and the diode starts conducting. And it's not. See, the whole curve is not. It's a curve. It's not a straight line. So depending on the voltage, the diode will behave different way, and things are not going to be proportional. They are all what they are when it comes to diode. When it comes to the reverse bias, yes, the same thing happens, but you need to apply way, way, way more voltage, and basically the diode is going to break down. It says, I can't resist anymore. I give up. And boom, the current flows, and usually the diode gets damaged when it comes to that, this region right here. All right, so let's see here. Other devices such as circuits like transistors can also operate in a non-linear way. However, sometimes if you, let's say, I zoom this thing here. That's as far as I can zoom. Somewhere here, you may find something that almost resembles a straight line. Then you might dress up the circuit and that component inside that circuit that you could use that part of the curve that almost looks like a straight line. Of course, we're not doing this thing with diodes because this thing is just the change is happening just too rapid. But with transistors, we can. We can find something that's called quiescent point, which is going to be something like, for example, a transistor curve. Let's forget this is a diode. There's going to be amplification going on here. So there's going to be straight line or something that almost is a straight line. And if you want to send a signal to the base of the transistor, then we're going to have a current flowing through the collector, and it's going to be amplified in a linear way as long as we operate within this region. And the quiescent point is going to be the medium point right here. So we can go that far from the center and that far from the center and stay within the so-called linear region of the transistor. We're going to talk about that further down the road. All right, so let's see here. Here we are. Other factors that affect linearity and again compression, clipping, biasing, and temperature. Yeah, so if we bias the transistor, let's not get ahead of ourselves. Okay, reaching the quiescent point would be biasing the transistor. We'll talk about that too. Now, here's a question for $64. Let's see here. Can 100% linearity be achieved? Question mark. This can be very difficult, but typically linear circuits are very close to being linear, and we may specify a voltage, frequency, or temperature range or other parameter where we expect the circuit performance to be linear, which is exactly what I was just talking about, a few seconds ago. All right. Next slide, please. All right. Now, phase linearity. We talked about voltage. We talked about current. Well, what about phase? What's phase? Well, a phase. Okay, I forgot to power up my my whiteboard. A sec here. just so I could start drawing things, because sometimes I like to draw pictures, just like reading a book, just reading the letters. All right. New file. Let's say things are getting slow. All right. Let's get this one here. Create. Okay. So let's see. Let's say we have the X and Y axis. So here's a Y axis. Here's an X axis. Let's say this would be time. And this would be voltage. So just like on the oscilloscope, let's say we have some sort of a waveform going on. It's a sine wave. And we know it's a sine wave because it starts at 0. And if it started at 90 degrees, there will be a cosine wave. But we're not talking about cosine waves. We're talking about sine waves. So let's say here's a signal. And so here would be 0 degrees. Here would be 180 degrees. And here would be 360 degrees. If you studied I'm pretty sure you have studied some AC theory by now. So this here is, well, it's a waveform, starts at 0 and repeats after 360 degrees. Now, let's say we're going to have something like another waveform that starts here. And it's going to be the same. Let's get a different color. This other waveform goes like this. I hope I didn't, yeah, pretty good. Let's see over here. So the beginning of this waveform, when it crosses from 0 on the y-axis, it starts here. It starts 90 degrees later than the first waveform. So we can say that the red waveform is phase shifted 90 degrees from the original waveform. Phase shift is a quite significant phenomenon and cannot be ignored. We'll talk about that more. All right. So the phase shift, okay, linear phase shift can happen. Linear phase shift, okay, versus nonlinear phase shift. Now we're getting a little bit tangled up in our thoughts here. Let's see here. A linear phase shift happens when the phase response of a device or a circuit is linearly proportional to the frequency. So here is a bit of a graph. Now, it looks a little bit intimidating, but let's take one thing at a time. Here is the frequency on the x-axis. And this one here says phase and voltage. So this one here, let's take a look at this as a phase. So forget that this is voltage. Let's just say, because there are two graphs on one. Right? So ignore this, ignore the phase. Let's just say this is the voltage, this is the frequency. So as the frequency, phase, forget the voltage, phase, because we're talking about phase shift. So as the frequency increases with certain circuits, the waveform across different components can start separating in phase. They can have a phase shift. So let's say if the frequency increases, the phase shift between those two components changes, but it changes linearly. We get the frequency goes higher, then the phase shift is that much. Frequency goes higher, then phase shift is that much. And if we get a straight line, then we're talking about linear phase shift between components. Okay, so linear phase shift happens when a phase shift response the phase shift responds with the change to the changes of the frequency. So when the phase shift response to a device or a circuit is linearly proportional to the frequency. The phase versus frequency when displayed is a straight line. We have a straight line linear phase shift happening as the frequency changes. For a purely resistive circuit, this would be a flat horizontal line. You just have a resistor, then the phase, there's no going to be a phase shift. For inductive or capacitive circuits, well, things are going to react. And inductive and capacitive components are called reactive components because they react to the frequency changes. The impedance changes. They have reactance. A reactance is a resistance, but it depends on the frequency that is applied to that part. So that's called, instead of calling it resistance, we're calling it reactance, which is basically reactive resistance. So for inductive or capacitive circuits, this will be a straight line going diagonally. And capacitors or coils, they may respond in the opposite way, but nevertheless, you're going to have a straight line. Let's see, what could that be? This line here, could it be capacitive or, well, I'm not going to get into that yet. All right, in practice, devices and circuits delay some frequencies more than others, resulting in a nonlinear phase shift, creating a distortion in multi-frequency signals, including data, square wave, switch data. So that determines the speed with which we can send data. It limits our speed because when there's a certain type of signal and the signal is being timed, and when the timing is being delayed, depending on the frequencies, then we can only have so much bandwidth per channel. And when the frequencies shift too much, or the waveforms shift too much, they're being undetectable, or the signal is going to be mistaken for something else. So within the tolerance, by the tolerance that we set by the equipment, and maybe we're going to have so many channels from one frequency to another, from one frequency to another. If that information shifts too much and it hits the other channel, then, well, we might have problem with the transmission. Okay? In practice, devices and circuits delay some frequencies more than others, resulting in a nonlinear phase shift, creating a distortion in multi-frequency signals, including data, square waves, which are not made of multiple, so which are made up of multiple frequencies. So we get a square wave being transmitted, and square wave consists of many frequencies composed into that square wave shape. Then we might get completely different shape at the end if the frequency response is, or the phase shift is non-linear. Right? Non-linear circuits, amplitude, voltage, current, or phase can cause distortion, including mixing and harmonic frequencies. Linear circuits do not produce any new frequencies or harmonics. We're going to come back to understanding this thing a little bit more as we do the labs. And I'm going to try to remember to remind you that. All right, amplifiers. Simplest amplifier is a bipolar junction transistor. I'm not sure if you have done the lab, that it will be the class A amplifier. BJT, bipolar junction transistor, which is a current amplifying device. In the linear mode of operation, the current at the collector Here's the base, here's the emitter, here's the collector, and we're talking about NPN transistor here. Excuse me. So depending on the base current or the voltage of the signal, which causes the current changes, we're going to have current variations in that transistor. Now, this amplifier is made so we could use as much of the linear region as possible. So let's see here. In the linear mode of operation, the current at the collector, here's the collector, is a multiple of the base current. Here's the base. What is the multiple? This is the gain that we're trying to apply here. And the gain we describe as the Greek letter beta. Beta varies considerably from device to device, so the beta in the BJTs are not equal to each other, and sometimes you want them to be equal if you're going to get a B-class amplifier. But A-class amplifier, if you replace one transistor that is the same with another, the same one, then you might get one with slightly different beta, and beta is the coefficient of amplification. And of course, so what is the gain of the transistor? It would be the output current divided by the input current, and that is going to be the gain. Right? So the beta, which is the internal type of a parameter of a transistor, from one transistor to another, it varies even if they are the same transistor, the same marking on the transistor, the same type of a transistor. So what we're trying to do here is we're trying to dress this up so the transistor amplifies, but the beta of the transistor is not playing as much, making not as much difference as the components that are surrounding it. So beta varies connection of the device as well as the temperature. So the design of the amplifier circuit is used to set the gain. In this example, the DC gain. DC gain, forget that capacitor that is here. It's a bypass capacitor. So in this example, the DC gain is set by the ratio of the RC to RE, the collector resistor and the emitter resistor. If you take this one, the value of this resistor, and divide it by the value of that resistor, you're going to get the gain that this transistor is going to give you. So then we're bypassing. I don't want to use the word bypassing because here's the bypass capacitor, but we're trying to make this beta not as significant when it comes to the controlled amplification that we're trying to achieve. So for an AC or small signal device, so for AC signals, we need to consider a capacitor, this one right here. So for the DC amplification of the DC, gain or amplification of the DC component, these two resistors are fine. And it is going to give you some gain for the AC as well, for the AC signal. Let's see, here's the AC signal, and it's going through the capacitor that strips the signal of any DC component that you could have. And here these two resistors are biasing. It's a voltage divider between the VCC and the VCC. The CC stands for collector, because many of those transistor circuits, they have more than one transistor and they have many collectors. So this VCC, it stands for collector. Same as for the FETs, they are drain and source, so VDD, okay, or VSS. So we're setting up a voltage divider, and we're setting this point at a certain voltage, that this base is going to sit at a certain voltage, And that is going to determine the quiescent point, which is the point that we can take it up or down without entering the nonlinear operation of the device. Why do we need that bypass, AC bypass capacitor? Well, it will have different reactance when a frequency is being passed through it. So then the gain is between this resistor and this reactance. And it's going to be a bigger difference. So the gain, as soon as you put that capacitor right here, the gain, the AC gain jumps up 100 times more. So that's why we have that. So the gain goes between this resistance and that resistance for the DC. And yes, it will give you some gain for the AC circuit as well. But in order to improve the AC gain, we are putting this one here in the circuit, in the picture. Then we're talking about this reactance and this resistance. So this divided by that is going to give you much higher gain when it comes to AC signals. So for AC or small signal device gain, we need to consider the capacitor, the emitter capacitor, also called bypass capacitor. And pretty sure that at some point you have done the Class A amplifier lab. If you haven't, let me know. The resistors R1 and R2, I would just say, are forward biasing the quiescent point, which is this one right here. That's the quiescent point, the Q point. So here is the current on the collector. Here's the voltage of the collector emitter voltage. You are varying that which is the current on the base. In order to achieve that, here's the big current here. Or wait a second. Yeah. And you're trying to use somewhere here. So this amplified collector current can be much, much bigger. And we're trying to have an equal kind of a signal. So if we have this type of shape, we're going to have this type of shape on the output. Right. If this we were operating with outside of the linear region, then this shape would result of a different shape on the output. So here we're trying to have a linear region of this. So that's why we're setting up the quiescent point. We're setting up the base biasing the base so we can operate within the linear region of this operation of this transistor. We're trying to not get out of there. So this is a Class A amplifier. Okay, this amplifier is known as Class A amplifier since the transistor is conducting in over the whatever that 4 is here, 360 degrees. There must be some kind of a typo here of the input signal. And next slide explains what I mean here. This allows the device to deliver a linear operation for the most signal sources. However, it is the least efficient type of the amplifier. A sinusoidal or square wave at the input will result at the same signal on the output, with gain set out by the collector emitter impedance ratio. See, we're talking about the impedance now here. The impedance, which is basically a resistance here, over the impedance here, this divided by that is going to give you the gain. And with this one here in picture, that impedance becomes much smaller than this resistance or the impedance, which is basically a resistance mostly. Then, of course, the gain is going to be bigger. In this example, the capacitor, the emitter will increase the gain, all the devices have frequency limits. And each circuit design will also, what is it? All devices have frequency limits, and each circuit design will also alter the frequency response after typo again. Other amplifiers. Here's the class A because it operates within the 360 degrees. Right? Notice that it inverts. Right? So if you want same kind of a signal, you need to use two of those, which works fine because one can be used as preamplifier to boost the signal for the bigger one, heavier one to work. So you're inverting the signal, you're inverting it back, so you have signal not inverted at the other end. But class A works within 360 degrees. Here's 0, 180, 360 degrees. Class B uses two of those and one transistor, PNP and NPN. Here's PNP, here's NPN. One takes care of the top half of the signal, and the other one takes care of the bottom half of the signal. Makes it more efficient because this one has to work less. It only cares about the top half. This one cares about the bottom half, and you could use the quiescent point to amplify more signal. Okay. The other thing is that these have to be matched transistors with the same gain, internal gain. If you have mismatched, you're going to have a little bit of a crossover distortion with the signal crosses from the top half to the bottom half. You're going to have a bit of a hiccup here. But if those transistors are matched of the same gain, the internal gain, then that is going to be pretty much a straight line. Never get perfect though. So that's how the class B works. These two pictures describe class B. Here's the 360 degrees. This one takes care of the top half. This one takes care of the bottom half. And on the output here, they are joined together and we got, so it's more, you got the same signal here, but they share top and bottom half. And there's class C amplifier that basically operates just a part of the signal, and usually is used for oscillators and pulse generating circuitry. Now, lab example. The following is an example of class A intermediate frequency amplifier, IF. Okay, intermediate frequency is a modulated frequency in a, let's say, radio receiver that all the amplification systems, the transistors and all that are set to that carrier. And that carrier is set for the whole circuitry of the system. Now, different channels are coming into the receiver, and that carrier frequency with the modulated signal is first transferred into the intermediate frequency, which is constant always, and then the signal is being stripped. I shouldn't be pointing at this. Then the signal is being stripped of the carrier, and then just the intelligence signal, so is being transmitted through the loudspeaker. Right? So let's see here. Following is an example of a class A intermediate frequency amplifier. We will be building in the lab, but here's the red print. It uses a tuned primary transformer instead of a resistor of the collector. So here, instead of this resistor, we're going to have a tank circuit, but it's called the 450 kilohertz transformer, which is the IF, intermediate frequency for the AM transmission. And that thing is tuned to 455 kilohertz. and you can buy those. However, we have changed the labs a little bit. And I'm not sure if you've learned how the tank circuit works in AC theory. Have you studied tank circuits? Just someone dropped the line there in chat line, just so I know. If not, I'm going to explain things further. So here's a tank circuit. So instead of that resistor, here's what when things are happening. Now, tank circuit is tuned to a specific frequency that it resonates. And once that frequency is applied to the whole circuit, then the whole thing becomes alive. It's the frequency, the resonating frequency of that tank circuit is going to produce a huge, huge signal. And that's what we want to accomplish in that amplifier that is supposed to work with just that frequency. So we have that signal producing stage here. And here's our load connected to the output of that transformer. And here's the rest of the components that are composing the Class A amplifier. However, instead of using the IF transformer, because, well, they're becoming scarce a little bit and they're so easy to damage, and we have encountered so many problems slowing us down, we have decided that we're going to build this circuit, which is pretty much the same thing, but this one you have to buy, and it's very fragile, and you can destroy it without even knowing it, and then the lab doesn't work, and you're losing a lot of time. But this one here, you're going to be building out of a capacitor and a coil, and you'll be giving a frequency in which you want to be operating, based on whatever. Everybody's going to get different frequencies, so people not copying their labs. So you are actually learning instead of not learning. You're going to be working with your own frequency in that lab. That's going to be further down the road. That's lab 5. And what do we see here? We see the components of the Class A amplifier. Here's the base biasing voltage divider right here. These two resistors, R4 and R5. There we go. Here's the transistor. And here is the collector part of the Class A amplifier. Here's the emitter part. And here is our load right here. And those TPs, TP stands for test point. We're going to, we'll be referring to the TP, whichever number. And we're going to ask you to, well, see what signal you get and record that and put that in your lab report. And over here at the input, what do we have? Remember the first mixing stage? So here's the carrier. So that's going to be high frequency in kilohertz. And it is going to be tuned. That frequency, actually, this tank circuit is going to be tuned, or the resonating frequency is going to be calculated. So you're going to have to choose appropriate parts in order to accomplish the resonating frequency by request. And then you're going to set the function generator to that frequency. So this whole thing is going to just cook with gas. Other frequencies are going to be amplified too, but not as much. And we want this thing to be most efficient. And then we're going to garnish that carrier frequency with another signal or another function generator. And that's going to be our modulating signal or the intelligence signal. You could put some music through it, but we don't want to do that because you wouldn't be able to study the waveform. So we're going to put a test signal, a sine wave. That is going to be low frequency sine wave modulating the higher frequency sine wave. Basically, that is going to be nice and pure sine wave until this guy comes in and screws everything up. Right? It's going to put this guy out of shape. So in a specific sort of way. then you're going to have that voltage divider is so going to set the proportions of how much of the carrier and how much of the modulating signal you want to combine or mix in order for things to be not distorted. Because if you overmodulate the carrier with too much signal, then you're going to have distorted signal on the output. But if you have not enough carrier, then you're going to have a signal that's too weak. All right, so it's undermodulation and overmodulation. And that's going to be the lab. We're going to have some fun doing this lab. Fun, quote unquote. You're going to get frustrated with some of the labs, for sure. But then once you get this thing right, you're going to have that satisfaction of overcoming the challenge. All right. And now we're going to have something that's called operational amplifiers. Here's what an op amp looks like, operational amplifier. We're going to spend some time on that little guy here. And we're going to have some fun with this guy. The operational amplifier is known as linear amplifier with many different uses. Woo, again, opening statement. Each amplifier contains many components to achieve high gain and linearity. Well, that guy here looks like this inside. You see here, you have the inverting input, which is marked with the negative sign. You have the non-inverting input, which is marked with the plus sign. And you have the output. If you put your signal to the inverting input, let's say you get a sine wave like this, you're going to have a sine wave like that, inverted, well, 180 degrees. 180 degrees out of phase, all right? On the output. If you apply signal to the, if your main signal is to the non-inverted input, then you're going to have a non-inverted output. Sometimes you want this, sometimes you want this, and sometimes you want both. And this is an active device because it needs to have power applied to it. So here, don't forget to apply positive power to the pin 7. We're going to apply the negative power, and some of us already have accomplished that plus 15 volts and minus 15 volts on connecting two outputs of that power supply. That's why we're practicing that. We're going to do some more of that this week during the lab, just so everybody's comfortable with doing that. So we're not wasting time trying to learn how to establish the power supply. And the point between positive 15 and negative 15 volts is going to be the midpoint, which should be 0. And we call it a virtual ground. Why we call that why do we call it virtual ground? Because it sits at the ground level as far as potential, but it's not electrically connected, not necessarily, not connected to the actual ground. There are some other pins that at this point we're not going to talk about, and this is basically to set that 0 point within that circuitry. It's called offset null. At some point we're going to have opportunity to set that, but usually we won't need that. But I also at some point I'll show you that because it's there, and I want you to know that this exists. And sometimes you do need to set that 0 point. Okay, so here is that operational, the schematic diagram. Look, here is the non-inverting input. Here is offset null we just talked about. Now where's the pin 2? It's somewhere there. Can't find the damn thing now. What's going on? It's somewhere there. Not gonna spend time looking for it. I know it's there. Here's the output. Here's the pin 7, which we are going to apply positive power, negative power. Still looking for that pin too. And here's the pin 6, that is output. Now it's bugging me. There's pin 2 right there. Inverting input. Okay. And this is how it relates to the symbol of the operating amplifier. And that little triangle pointing one way, that's the symbol of an amplifier in electronics schematics. All right, operational amplifier, power connections. Here's your reference. See, we are joining two power supplies like this in series. So the point in between, over here, we're climbing up, climbing up, climbing up, and that's going to be our plus 15 volts. Well, sometimes you can design a circuit to be plus 9 volts or whatever other volts, but we will be working with 15 volts here. But look, from here, you're going down. So you go down, 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 down. It's going to be minus 15 volts. So here's your positive power supply rail. Here's your negative power supply rail. From here to here, what do we have? Here's the 15 volts with the plus and minus that way. So from here, we got 15 volts. And then we got another 15 volts. So from here to here is going to be 30 volts. And the point in between is going to be dividing that. So from here, we're going to go up 15 volts. And from here, we're going to go down 15 volts. And this is going to be the point in between, the middle. And it's called virtual ground because technically it should be at the ground level. Excuse me. But it's not necessarily electrically connected to the ground. It can be. Now, just so you know, this is one of the types of the operational amplifiers. There are different types of op amps, and some of them are designed to be connected from positive power extreme to negative power extreme. And some of them are designed to work with only one power supply. But for the most part, we're going to be working with these. Also, I put this thing here. Pay attention while connecting your circuits, because sometimes this amplifier is going to be drawn like this, with plus on top, negative on the bottom, which is the non-inverting input. Here's the inverting input. And sometimes they're going to be drawn like this. Non-inverting input on the top and inverting input on top and non-inverting input on the bottom. So always pay attention when connecting the circuits. And there's no rules of how this thing should be drawn. All right, there are certain rules for the operational amplifier, and I'm not going to give them to you now in as structured way as I'm going to give it to you later, because I want you to think a little bit first. The ideal op-amp has a very large open loop gain. What's an open loop gain? Open loop gain is without any dress up. There's no components connected. Here's the amplifier, here's the power supply, and here's the power supply. You see, some of the op-amps use transistors, circuits, and some of them use MOSFETs. Well, if it's a FET type of a circuit, then we have if it's a transistor, we're going to call it VCC. And if it's a FET circuit, then we're going to VDD for the drain and source. Yeah, that's as simple as that. Now, if it's an open loop, if this thing is just standing on its own, let's say this positive power supply or a positive power supply is plus 15 volts, and a negative power supply is negative 15 volts. So here's what's going to happen. It kind of compares these two. Inside, the circuitry compares the potential of these two. If there's no any additional parts, if this potential, this point is slightly higher than that, then the output is going to go all the way to the power supply. So if we are having 15 volts, then this thing is going to go 15 volts. We call that as infinite gain. So, well, does it mean that if we have 5 volts, then it's going to take this thing to infinity? Well, if we had the infinite power supply, yes, it would. But it's going to go only as far as the power supply is going to let us, right? So it's going to go right to the saturation point, to the plus 15 volts. Now, if this one right here is slightly higher than that one, it is going to go down all the way. And it's very difficult to sometimes accomplish slightly more than 0 and slightly less than 0 volts. So this is not a very stable circuit, but that's how it behaves. Also, we should know that there is no current flowing in to any of those inputs, and there is no current flowing out any of those inputs. So the impedance, the input impedance of that amplifier is ideally infinite. In reality, yes, there's going to be some small amount going if you really want to, take it that way. And yes, sometimes we need to consider that. But in reality, our reality, we're going to consider that there is no current flowing in and no current flowing out any of the inputs. It helps us, that knowledge is going to help us tremendously when doing some complex calculations. So just remember that. Now, ideally, the output impedance is going to be 0, but it's not. Close to. Because we want to have as much possibility of a current flowing without any obstructions. And that's kind of not all the rules here that I gave you. So ideal or typical. Yeah, all right. So input resistance is going to be infinite. Typically, well, 10 megs to 10, whatever, tera it is, 12, whatever that is, 10 to the 12 ohms. That's a lot of ohms. Okay. Input current, 0. So this current here, why do we have an arrow here? Wow. There's going to be other parts connected to it, so the current is going to flow through those parts around it, but not into the amplifier, not out of the amplifier. So that makes a pretty good buffer too. If you want to isolate 2 pieces of equipment or two stages of a circuit, then that's a pretty good thing to use that. You can have a unity gain amplifier, so you have 1 volt on the input and you have 1 volt on the output. So why bother using the damn thing? Well, the reason for using that, if you want to isolate electrically that part of the circuit and maybe that part of the circuit as well. Output resistance, ideally 0. Typically, yeah, see, it's not 0. Anywhere from 100 to 1 kilo ohm. Gain, infinite. But we know the gain is limited by the power supply. The voltage on the output cannot go any further right, than the power supply. It just can't. Also, one other rule, and we're going to give you this thing listed here, right? That amplifier, the circuitry over here, inside, is going to make its darnest that these 2 voltages are going to be the same. So for our calculations, just remember that. If you have one of those inputs hard connected to any kind of voltage or power supply or ground, then we know for sure what the voltage is going to be on, for example, this one here, which means it is going to be the same here. So if that is connected hard to a hard ground, then we know that this is also at the potential of hard ground. If we have a voltage divider on this one that brings that to a hard 5 volts, then we know that this is going to be hard 5 volts. It helps us a lot with circuit analysis and calculating things. Now, this rule is only if the calculated gain is going to be no further than the supplied voltage. So let's say we have a circuit dress up around that, and the gain of that, which is basically the gain, is the output voltage divided by the input voltage. And that's giving us the gain. So if we have 10 volts on the output and we have 5 volts on the input, then the gain is 2. 10 divided by 5 is 2. So if we have, let's say, 2 volts here, and the gain determined by the combinations of the resistors and the connections here, and the gain is going to be, let's say, 2. And the power supply is, let's say, 10 volts, for example. So if we have 2 volts times 2 because of the gain, we're going to have a calculated 4 volts. Is 4 volts as much as the power supply? No, it still have room to play because we can go up to 10 volts because that's where the power supply is. All right, let's say we get 5 volts here. We're getting close because 5 times 2 is 10, so we're getting close. And that's the last stage that we can amplify this. We can signal that strong that this rule about those 2 voltages are being the same applies. If the calculated voltage, like for example, if the power supply voltage is plus 10 and the gain here is 2, so if we have 7 volts on the input, then the calculated voltage here is going to be 14, but it's not going to get to 14 because we only have 10 volts supply. So it's going to go only up to 10. Then that rule about those 2 potentials, those 2 inputs equal, then it goes out the window. We'll talk further about that. I'm just giving you a heads up on that. Okay? Bandwidth is supposed to be infinite, but, well, in the ideal op-amp, operational amplifier, but it varies depending on the components used and whatever it is. So usually it's going to be specified in the data sheets of that. So that's why some of the amplifiers are better for certain things, like some of the better frequency amps, better frequency response with higher bandwidth are better for some high quality audio circuits. Did I miss anything? Let's see here. Sometimes referred as okay. So sometimes this thing is referred as differential amplifier. All right. The amplifier, the output amplifies the voltage at the inputs. What did I just say? That these 2 are going to be the same. Well, yes, they're going to be the same. But the amplifier is going to amplify of what the rest of the circuit before it hits the input, of what that is trying to accomplish. It's going to try to make things different, but this thing is not going to let those make different. It's going to react with the rest of the circuitry and it's going to apply the difference on the output. So a differential amplifier, it is what it is. It is going to amplify the difference that the rest of the circuit is going to try to make it different. And it's going to react to it by changing its output, so everything else reacts. It's one of the awesomest things, because let me just show you something. Give me a sec. No, that's not what I'm trying to get. Da, 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 da. All right, here's an audio example. I multi-simmed um, this. So I'm going to show you two circuits that I actually assembled in multi-sim. So circuit, one of the circuits I have, you don't see it yet. So this thing is with the noise. And this thing with no noise. So first I'm going to show you with no noise. Okay. There's the multi-sim. Okay. Here's an operational amplifier. So here's the non-inverting input, here's the inverting input, and here's the dress up. Now, here is a positive power supply going here. We got 15 volts. Here we have negative, here's the negative 15 volts. Here's the positive 15 volts applied. So pin 7 positive, pin 4 negative. Okay. Here's the output. And here are, I drew two generators that are 180 degrees out of phase. Okay. So this one here, this is getting this kind of waveform, and the other one gets the mirror image of the waveform. And if you get the mirror image of the waveform, which is happening on something that's called a balanced microphone. So pin 3 is inverting. If you speak to the microphone, or if you put like a sine wave generator output speaker, you're going to have the inverted waveform. And over here on pin 2, you're going to have non-inverted, and here's the virtual ground. That's why we have 3 prongs on those professional microphonies, okay? Or microphones. All right. So we're having a mirror image being supplied to the, so here's signal, and here's mirror image of the signal. Let's see what the oscilloscopy is going to show us. I'm going to turn that thing on. Oh, look. We have one signal on one pin. We have the other signal, just a mirror image of that on the other pin. So that thing called differential amplifier, which amplifies the difference between those two, or what the circuit is trying to make a difference. If you put a voltmeter here and here, you're going to have the same thing. But it's trying to make it different, and the trying of that is going to be amplified. And that thing is considered as a signal. Okay? Signal is being amplified. Now, let's add noise, but the noise, I'm going to add 2 more generators here, and I'm going to put them in phase. So, well, if you have a cable with the balanced signal, which is basically the inverted signal on both pins, if that cable is subjected to noise, let's say a Volkswagen drives by. Thank you, Mr. Powell. The forever joke. Then I keep using his jokes a lot. So those 2 cables are going to be affected the same way, because the noise in one wire is going to be in phase with the noise in the other wire. So they're both going to raise at the same time. And that is going to be ignored. So that's why the balanced line, it's called balanced line because we have 3 pins. One signal goes one way, one signal goes the other way. It makes it a balanced line. It's called balanced audio line, for example. Let's see here. I'm going to close that, and I'm going to get the other one. with, did I just close with something I'm not supposed to? With noise, with noise. Okay. Yeah. Just gonna open again. All right. Now we still have that signal. And this signal and that signal, these are the same waveforms that it's just a simulation of a signal. So these two waveforms are out of phase going in there. They're going to be amplified as signal. And here's noise that goes same way on both lines. So the noise goes in phase. And the noise is supposed to be ignored, right? Let's see if it does. If it is. Oh, look. Here's a noisy signal on one line. Here's a noisy signal on the other line, here and here, but they both rise and fall at the same time because they're in phase. So those are being ignored. The noise is being ignored. And on the output, we have a same, just clean, pure audio waveform. That's why in professional audio, for example, balanced lines are being used a lot because over the balanced line, you can send a weak signal over, well, considerably what is considered a long distance, which would be 200 feet, 300 feet. Weak signal can travel full of noise and could be still pure and nice and quiet as far as noise on the output. The only noise would be the noise that is going to be introduced by the circuitry, and you can't skip that. And some of the high quality equipment are low noise anyway. So that's how we accomplish that. So this is one of the uses of the operational amplifier. Keep going. Keep going. Here we go. Just make sure that I have that thing. Sorry, Mr. Bailey, I'm going to have to ignore you for now. Having a lesson. All right. Operational amplifier basic circuitry, negative feedback. All right. With the use of negative feedback, we can create a stable circuit blocks because if there was an open loop, which nothing connected, remember, if this one is even slightly higher, then the whole thing is going to go down all the way as far as the power supply is going to let it. And if this one is slightly higher, then the whole thing is going to go up as far as the power supply is going to let. But if we dress it up with circuitry, we can control that, how far it's going to go. Just like we saw that on the amplifier example. All right, so let's see here what's been written here. With the use of negative feedback, we can create a stable circuit blocks with defined transfer function or output as function of the inputs, which means we can control the output the way we want to. Okay, so below are several basic configurations. Unity gain, used to transform a high impedance source to lower impedance. The output attempts to do what is needed to keep the input at zero. Here. Remember, you see that here is going to try, because the amplifier is going to try to make these two equal. So if this one goes up and down, this one is going to start to go up and down the same way. So we're going to have the same signal, not amplified, not attenuated, which means reduced. But since remember, one of the characteristics of the operational, the input impedance is pretty much infinite in the ideal amp. So we're going to pretty much assume that that is infinite. So there is no electrical connection between here and where the signal is. So that makes it a pretty good buffer. All right, non-inverting amplifier. Well, we have some circuitry here. We have the feedback resistor, and we have the input resistor, and we have the signal going into the non-inverting amplifier. So guess what's going to happen? The signal on the output is going to be in phase, which is going to be not inverted. A version of the input signal. But from the output, we are creating some sort of a negative feedback, and we're shooting this thing into the inverting input. So this thing is going to be controlled. So just hint, hint. This here, these two are trying to be the same. So you can almost join that and work it as a voltage divider. And the gain, the gain of this whole thing, the voltage gain, is going to be, here's the formula, and it can be derived, but we're not going to today. The ratio of the RF divided by our input, which is RF is the feedback resistor. Here's the input resistors, which is going to RF and RI. So divide RF by RI is going to give you a number plus 1, and that is going to be the gain. So if the voltage here is whatever it is, let's say 1 volt, the output is going to be the 1 volt times whatever this is going to give us. Right? Cool, eh? So that's the non-inverting amplifier. Now let's see here the inverting amplifier. The output is 180 degrees out of phase as the input. So it's just reversed, like a mirror image. Okay, so what do we have here? The input is provided to this point right here, and we have the negative feedback going from the output through these two resistors, kind of a thing. Usually, mostly for that through the RF, because that is connected to the input and output is connected to the input, so it's a negative feedback. And the gain is the same thing here as the AV, but it's just like, presented in a different way, so we can, analyze it easier by seeing both versions of that. Because the gain, what's the gain? It's the whatever the strength of the output or whatever the magnitude, in this case is voltage. So the voltage on the output divided by the voltage of the input, and that gives us the gain, right? If the voltage is amplified by 5 times, then the gain is 5, right? So let's say this is 5 volts and this is 1 volt. 5 divided by 1, that gives us the gain of 5. So here, the same thing is just expressed in a different way. The gain, V out over V in, is equal to the ratio between this resistor and that resistor, right? Well, almost. And that's what I really, really want you to pay attention to, is that little negative sign right here. Okay? Because it's an inverting input we are using. So if we have the gain of 5, let's say this resistor is 10 kilo ohms, and this resistor is 1 kilo ohm. Put this one divided by that, 10 kilo ohms, 1 kilo ohm, you're going to have the gain of 10, right? Almost. And in this case, almost right is wrong, okay? Because it's going to give us the gain of negative 10. Right? That really, really has to be not forgotten when doing our calculations. This can trip you over big time. Why do we? Oh, why do we have that? Again, it is because we're connecting our input signal to the inverting input. Inverting input inverts. Non-inverting input doesn't invert. Inverting, so formula type signals this phase difference is not an issue. For a stereo system, it is important for the two channels to be in phase. Well, sometimes it matters, basically what this one says. Sometimes it matters and sometimes it doesn't matter. Note, what's the note here? Supply voltages are typically not shown. Oh, okay. All right, so another, it's extremely important information here. When you're going to see schematics with operational amplifiers drawn, you're going to have, you see here, here's the signal, inputs, output, feedback, where's the supply? It is assumed that the power supply is connected. So when you're assembling the circuit on your breadboard, you got to make sure that the positive voltage is connected. The positive supply voltage is connected to pin 7, and the negative supply voltage is connected to pin 4. Otherwise, this is not going to work. Same as the NAND gate or AND gate circuit that you did, the TTL labs, it's not going to work if you don't connect power to it. Right? So it is assumed, okay, what's it? Supply voltages are not typically shown. The ground shown is a virtual ground, normally halfway between the two supply voltages. So don't forget to connect the power. Don't call me and say, "Oh, you can," but you know you're going to hear. Oh, it doesn't work. What do you get? I get nothing on the. It's just. Oh, did you connect the power? Well, that's what you're going to hear. All right. Now there are different type of arrangements that are called certain way, labeled as certain things. The summing amplifier is an inverting amplifier with multiple inputs. All right. You see, what's the formula for the inverting amplifier? The gain of the multiple of the inverting amplifier is this resistor divided by this resistor. So if you have 1 volt on the input, on the output, you're going to have 1 volt times the result of this division, this by that, which is 1 volt times the gain, which is V over, okay. This division gives us the gain. So that is this times the gain. All right. So here's a summing amplifier. Look what we have. We have the same thing here, but what did somebody do here? We have more than one resistor on that. Okay. Well, let me get my laser. Here. What do we have? We have a bunch of voltages applied here. Let's say DC voltages. And let's say there is a certain value of the resistor applied as feedback. Where is it going? To the non-inverting input. So we're going to, sorry, non-inverting, inverting input. So we're going to apply this formula for gain. All right, see that? Inverting input. So if we have 1 volt applied to this input, then we're going to have, let's say, okay, let's say we have a unity gain. All right. We have a resistor that is 10 kilo here, And all of those resistors are 10 kilo ohms. So 10 kilo, 10 kilo, 10 kilo, 10 kilo, 10 kilo. If we apply 1 volt, then the gain is to this point. The gain for that voltage applied to this point only is going to be 1 volt times the gain, which is 1, because 10 kilo divided by 10 kilo is 1. That's our gain. We're going to have 1 volt. Okay. If we have another volt here, then we're going to have on the output this result plus this result. So 1 volt here, 1 volt here is going to give us 2 volts, because on the output is going to be the 1 volt times the gain, which is 1, plus 1 volt that's applied here, times the gain, and this is also 1 kilo, so times 1. So we're going to have 2 volts on the output, right? And I can almost hear your thoughts saying right, wrong. What's the one important thing that we are forgetting? I just want to see if you're still there. Don't know? Look where this thing is connected. It's connected to the, there we go. Thank you, Matthew. All right. It's connected to the negative or the inverting input. So 1 volt plus 1 volt is going to give us 2 volts, negative 2 volts. If we have 1 volt here and 2 volts here, and the gain between that is 1, the gain between this and that is 1, we're going to have 1 volt plus 2 volts. That's going to give us negative 3 volts, and so on. That's why this thing is called the summing amplifier. It's a hardwired calculator that adds. Level shifting. We're almost done for today. Systems that have both DC and AC signal components are quite common and often not desirable. However, sometimes we do want that, sometimes we don't want that. I just showed you the example of the noise that was in the audio, but sometimes in the automotive supply, we want to eliminate that noise too, caused by the alternator, so the digital circuitry can function, and whatever other circuitry, radio can function without you hearing that alternator noise, you know. You can do some level shifting on the operational amplifiers, which basically here, that thing here is connected where? To the ground. So by that one of those rules, if the calculated output is no more than the power supply, then those two are going to be always equal. It's whatever else is going to change around and produce the output. So this thing is setting at the ground. If we apply AC signal here, let's forget that, just one input here, apply AC signal, then the AC is going to hover between top half and the bottom half, and in the middle is going to be the 0. All right, so it's going to be plus, minus, plus, minus. But if you put that at the 5 volt level, for example, then you're going to have the same signal, but it's going to hover not around 0, but it's going to hover around 5 volts. So it's going to be whatever the AC signal riding on the DC component, which is going to be determined by whatever this thing is sitting at instead of the ground. Right? So we can do level shifting. And we're going to do a lab that you're going to apply signal, and you're going to be able to have the waveform going up and down with the potentiometer. Okay. You know what? That's as far as we're going to take that. Pretty much, I just want that to settle, and the rest we're going to have another hour on Friday, and we're going to take care of the rest of those slides, which is going to be perfect. Right? Cool. If you have any questions, I hope you guys and gals stayed awake during the whole thing. And I'm going to see you during the lab and then during the next theory session. So please, as a final reminder, make sure that you bring your labs printed, so things are going to be nice and smooth. Okay, that's it for today. Love you, and you're wonderful, but not as wonderful as me. I'll keep always saying that. All right, have a good one, guys and guys.